So we're going to start talking about multiple regression. And this is going to be more of a high-level overview of multiple regression to get a full kind of theoretical feel for what we can do with multiple regression and to at least kind of address some of the issues and complexities with multiple regression. And before we even start talking about multiple regression in detail, you just need to recognize there are multiple ways to use multiple regression. So not only do we have the methodological questions, and by methodological questions, I'm referring to how you've designed your study, how you're measuring your variables, what type of variables are they? Are they categorical? Are they continuous? What is your outcome variable? What do you expect based on theory to be predictors? Those are all theoretical questions. When we get to multiple regression, we're getting to the first actual statistical test that also has questions that we have to answer theoretically before we can even run the statistical techniques. Multiple regression has multiple ways to look at problems, multiple ways to look at data sets. Now, some of the more complex statistical techniques we're going to cover in this class do what is called an iterative process. So an iterative process means there's multiple ways to look at the data, but the actual analysis itself is set up in such a way that the actual model looks for the very best solution. In other words, it runs all possible ways to look at the data behind the scenes and gives us a final solution. Now, those are usually more recent statistical techniques because they rely on computer processing power in order to do those multiple iterations. Multiple regression, it's old-fashioned. It comes from the day of hand math. And therefore, it is not an iterative process, but it is a choice process. In other words, we need to choose what kind of parameters we want to set on the model we're looking at. And again, the model, when we talk about a model of data, it's how are we defining the data and how are we thinking about it. So multiple regression requires us to make some decisions, and those decisions will affect the outcome of the actual statistical technique. So I think you want to just keep that in mind, that as we move to multiple regression, we're moving to the first actual statistical technique that requires us to make some informed choices. And those informed choices will affect how the data turns out. All the previous statistical techniques, we have to worry about what we're putting into the statistics. We have to worry about the methodology. We need to worry about, did we violating the assumptions? Are we putting the right kind of variables in? But once we put those variables in, we're going to get the same answer. This time, when we put those variables in, once we've made those decisions, depending on our choice of how we run the multiple regression, we can get different responses. So that becomes another thing we have to worry about. So again, simple versus multiple regression. Multiple simply means there's more than one predictor. Now, by adding an additional predictor, we also basically open up the door on a lot of possibilities. Now, with a simple regression, regression itself is a linear model, which means that by its nature, it's looking for a linear relationship. And if we only have one predictor, really, we have to only be looking for a linear relationship. So that's one of the assumptions. With multiple regression, we can always start with the very first predictor being the linear predictor, which means that the first thing we can do with multiple regression is we can look for then nonlinear results by putting in nonlinear potential versions of our IV into the actual multiple regression. And we'll talk about how we do that, but that basically allows us to look for higher order trends. And a higher order trend is a nonlinear trend. But in order to look for a nonlinear trend, we need to have the ability to add multiple predictors, and we need to look for the linear one first. So we can't do it with simple regression because we're only allowed one IV, one predictor. In multiple regression, we can start with that linear result and then create higher order nonlinear trends to see, do they explain more of the variance than the linear result. So the regression coefficients, what we're calculating, how we're calculating it, and also again the idea of how much variance is being explained. So the idea of beta, B weights, all of those are the same as we talked about in simple regression, but now they're going to be more complex in the fact that we have multiples to work with. As far as predictability, we're going to get better prediction with multiple regression because, again, human behavior is complex, and the more ways we can measure predictors of human behavior, the more likely we can come up with a very decent predictive model. We can also now look at categorical variables. Now, again, if we have categorical variables, it's not that we couldn't look at them with simple regression. It was simply a matter of why not just run a t-test. The reason we would have categorical variables here is we have multiple predictors that we all want in one single statistical test, one single statistical model. Now, those categorical variables have to be dichotomous. They have to be two-leveled. But we can even break up larger categorical variables into what we call dummy-coded variables, and we'll talk about that as well. As I said, higher order trends, which of course are nonlinear trends. We can also look at the interactions. Are multiple variables not only affecting our outcome individually, are they working in tandem to create a more complex model? We can look for that. Now, the final part of any multiple regression is, again, a choice of what is the model we're going to settle on. Now, in a computer-controlled model, an iterative model, and we're going to talk about some of those later in the semester and next semester, the model is being selected for us based on set criteria. In this case, with multiple regression, we have to go through individually and decide which predictors are we keeping in the model and which ones are we not. So for instance, we might do a multiple regression with 5 predictors. We run it through and we find that 2 of them are not significantly related to our outcome, but 3 of them are. At that point, we would select a model with only 3 predictors. In other words, we don't need to waste statistical power on non-significant predictors in that model. So again, not only are we making choices prior to running the multiple regression, once we've ran a multiple regression, there are also choices. So I've got the most common statistical technique that we actually look at when we run multiple regression. However, in this case, we're going to let the computer do most of that for us, and what we really need to look at is simply the prediction equation. We're still predicting y prime, we're still predicting it with a constant, but now we have multiple predictors, but we just basically keep adding them. So for instance, constant plus the b weight of our first predictor, plus their score on the first predictor, plus the b weight of the second predictor, plus their score on the second predictor, and onward for as many predictors as we have. So multiple regression suggests that there are 2 or more predictors, independent variables, that are related to our outcome. Now, these variables can include linear trends, just like simple regression. And in fact, they might be the only thing they include. We might have a good theoretical reason to only be looking for 3 or 4 predictors. They're all continuous. We have a continuous outcome, and we're all expecting them to be linear trends. That might be the sum total of what we're looking at in multiple regression, just multiple linear predictors. We can also look at covariates, though. So the covariate is the idea that we actually want to account for the variance of something and remove it. So again, because we're getting to choose the model, we can actually add a covariate. Now, normally we're going to do that in a technique known as blocks, where we remove the variance of our covariates before we look for the rest of the relationships. So one way to think about this is that a covariate is a variable that we think is making noise in our data. It's basically confusing the issue. Let's say, for example, gender. We might know that gender is somewhat related to our predictors, and it may also be related to our outcome, but we're not actually interested in gender differences for this particular study. We want to ask, if we ignore gender differences, do these outcomes predict, or do these predictors predict the outcome in people regardless of their gender? What we can do in a multiple regression is we can actually enter gender as the very first variable to be looked at, and basically set it to where it ignores that relationship. It removes it. It's no longer a part of the model. And then in an additional block, past when we removed the gender differences, we look at the rest of our predictors. As I said, of course we can use continuous variables, but we can also use categorical variables. If those categorical variables are dichotomous, 2-level, then we don't need to do anything to them. However, if they're not, we can dummy code them. And the idea behind dummy coding is, again, multiple regression allows us to have multiple predictors. So if I, for instance, have a categorical variable with 4 levels, I can create dummy codes, multiple variables, out of that one categorical variable. And what that basically represents is the first one is going to be either the presence, let's say it's 1, 2, 3, or 4. We're measuring something that we've labeled 1, 2, 3, or 4. The first dummy code is 1 or not. The second dummy code is 2 or not, and the third dummy code would be 3 or not. And you actually don't need to create the 4th dummy code, because the 4th dummy code naturally exists, because the or nots are going to be zeros. So the first dummy code, 1 or not, you're going to have a 1 if you actually had a 1 in the categorical variable that went 1 to 4. Any other number would be coded as a 0. The second number, you're going to have a 2 if you actually had a 2 in the data set. But again, any other number is going to be 0, and the final one is a 3 if you actually had a 3 in the data set, and any other number is going to be a 0. Which means the 4th the fourth number, 4, is represented by anyone that has zeros in all three of those. So when we dummy code, we actually get all of that data into individual dichotomous pairs. We can look for nonlinear trends. And to create a nonlinear trend, we have to actually create a new variable based on the original linear variable. So if I was measuring depression as a linear variable, I could do a mathematical transformation to that data set, those people's scores on depression, to create a nonlinear trend, and we'll go over how we do that as well. And finally, we can create interactions between multiple variables. We can create the interactions between two continuous variables. And remember, an interaction is basically the idea that if we have two predictors, let's say depression and anxiety, and depression is related to school performance, and anxiety is related to school performance. But if you're just depressed or just anxious, the relationship that they have with performance may be smaller than if you're both. In other words, if you're high on both, it may be an additive or even a multiplicative effect, where if you're high on anxiety and you're high on depression, not only do those have a direct effect on your performance, the interaction between the two has even an additional effect on school performance. That would be an interaction, and we again can create a term, an interaction term, and then enter it into the multiple regression. Now, each additional predictor variable means that we must now consider how the predictor variables relate with each other, as well as the outcome variable. So again, we can get into a situation where we start creating an enormous number of predictors, because a lot of these dummy codes, nonlinear trends, and interactions, we're actually creating new variables out of existing variables by either mathematically converting them, breaking them up into dichotomous pairs, or creating interaction terms in and above the linear trend. So for example, if I was actually doing a multiple regression using my example before of depression and anxiety on school performance, originally that would be a 2 predictor, 1 outcome multiple regression. If I created an interaction, it would now be a 3 predictor. I would have depression, I'd have anxiety, and I'd have the interaction between depression and anxiety. Now I have 3 predictors on a single outcome. If I wanted to also make sure there weren't nonlinear trends between depression and school performance and anxiety and school performance, I would then create a nonlinear single bend or curved line test of both anxiety through mathematical transformation and depression. So now I would have anxiety, depression, the interaction of anxiety and depression, the nonlinear trend of anxiety, and the nonlinear trend of depression. I now have 5 predictors on an outcome. So just recognize that multiple regressions can become fairly complex, and we want to consider these possibilities, but we also want to be taking a little bit of control and not adding variables just to add them. So the regression coefficient, interpreting the regression coefficient depends on the purpose of the additional variables. So again, adding a second independent variable simply allows you to test the relationship of a second predictor on the dependent variable, but we also want to make sure that's what we actually are wanting to do. So sometimes we may indeed be actually putting in 3 different versions of a variable. We may have, again, anxiety as a continuous variable. We may have the nonlinear trend of a curved line of anxiety, and we may actually even go further and create a double curved line, so one that goes upside down U followed by a normal sized U. So think of it as a kind of sine wave. We might test that as well. Now, we might not be expecting all 3 of those to actually be predictors of our outcome. We may be testing which one is the better predictor of that outcome, which means that, again, interpreting the regression coefficients doesn't mean that we simply add every single predictor into our regression equation. That which predictors we choose, which model we choose, depends on theory and also the results. We might also drop out, for example, non-significant predictors. So just because you have an initial multiple regression with 5 predictors doesn't mean that your regression equation, your prediction, A plus B1, B2, etc., is going to have 5 beta weights. You may actually end up removing a couple of those predictors because you find either A, one of them does a better job than the other, linear versus nonlinear, or B, one is not significant, or you may, much like we said, be doing actually one as a covariate. You're not intending to ever use it for prediction. So again, these are not choices that SPSS makes for us. These are not choices that if we hand calculated a multiple regression we'd be making. As far as statistically, they're a user decision. We're deciding what we're going to use. So when adding additional predictors, do consider power. So the more predictors, the less power we have to find differences. And the reason for that is it reduces the degrees of freedom. And the smaller the degrees of freedom, the bigger the effects are for us to claim statistical significance. A general rule of thumb is you want at least 10 subjects per variable in a multiple regression. So for instance, if you have two variables you're measuring, anxiety and depression, that would be you'd want 20 subjects. And actually, I would say include your outcome as well. I would say you'd want 30. So we have 3 total variables, 2 predictors and an outcome. Let's go with 30. But you know that you're also going to look for the interaction term, and you also want to look for those 2 nonlinear terms. So you're actually at the end going to have 5 predictors on an outcome. In that case, I would suggest a minimum of 60 subjects. Now, I'm going to also go one step further and say that especially for your thesis or any research you're planning to publish, I would double that number. I would go a minimum of 20 subjects per variable as a rule of thumb. Now, there are programs online. There's also programs you can buy that do what's called a power analysis. And basically, you can put in, based on previous studies and the power of the relationships they found, in other words, how strong was the relationship between anxiety and school performance, you can actually calculate how many subjects specifically you would need to find the effect size that you're looking for. So that is another way to look for power. And again, I would generally say that whenever you do a power calculation, you always want to go above and not below what's calculated. But an easy way, again, is just this rule of thumb. One thing you also want to consider before ever running your multiple regression, while you're actually creating your study and methodology, is the problem of multicollinearity. Multicollinearity is when you have multiple predictors, or IVs, that are too related to each other that may still be related to your outcome. They're basically potentially measuring the same construct or different variables that are somewhat very similar. And the problem with this is that once we actually get to, again, the math of the multiple regression and the choices we make on the type of model, they can seriously alter the regression coefficient. So for example, the top graph there on the right is a Venn diagram of moderate collinearity. We have a predictor X and a predictor W on Y. And you can see that there's a fair amount of variance that's predicted uniquely by W. That's the green. That's the point where whatever W is, we'll call it anxiety, is predicting school performance. And X, depression, the blue section, is what it's uniquely predicting in school performance. Now the red section is the overlap. That is being predicted by kind of both of them. Now again, depending on the type of regression you run, that red section may be given to W, it may be given to X, or it may be removed from the equation and ignored. It again depends on the choices we make. Now, in this case, we're going to get slightly different answers. If it's red, W is going to be the bigger predictor. If red goes to W, W is going to be the bigger predictor of the two. If the red section goes to the X, orange section, it adds to blue, and now X is the larger predictor. But both are probably still significant. And if we remove red altogether, both W and X will be seen as less powerful predictors, but both of them will still be seen predictors. Now, what happens, though, if the red section is a lot larger? And that's what happens with multicollinearity. In this case, if we actually ran a multiple regression that ignores red, we might actually find that X and W statistically are not related to our outcome, which is actually not the truth. If the red section is given to W, we might find that W is significant and X is not. And again, if the red section is given to X, we might find that X is significant and Y is not. So we're in the top example, we might get slight differences in the effect sizes. We're probably not going to get a different answer to which predictors predict outcome. With multicollinearity, we're going to get different answers. We may get neither of them are predicted or related when they are. We might get that one is predicted but the other one isn't, or vice versa. So one of the things we're going to be looking at, and one of the assumptions of multiple regression, is that our predictors do not have multicollinearity. And we'll talk about some of the rules of thumb with that as well. So predictive variables can be entered into the model several different ways, and this is again one of the choices we make. The first way we do it is basically just statistical, and not only that, it's not just statistical, it's basically the way that multiple regression worked right when it was created, though this is historical almost. I would generally suggest that the only time we use standard entry, where we're entering all the variables all at once, is if we're doing exploratory analysis. Because what happens is that every variable competes with variance, and the common method when all variables are deemed as equally important. So if you have no theoretical reason to believe that certain predictors are going to be better or worse, if you have no theoretical reason to expect nonlinear trends, if you're not expecting interactions, and if you're not expecting nonlinear trends, all of those would be situations where you could possibly run a standard regression. Now, the big problem with standard regression is this is the one that ignores shared variance. So you're always going to get smaller amounts of explained variance compared to the other methods. The next technique is one at a time hierarchical, or given in blocks. So now this is the example of this is when you have solid theoretical reasons to expect relationships. And you as a researcher are going to control the multiple regression. So this is definitely the technique you'd use if you're doing covariance. If you have covariates, you're going to enter those in the first block. You're going to create a mini model with just the covariates, and you're going to tell multiple regression, run this first, and then once that variance is explained, remove all of it from the equation. And now I want to ask, do my predictors still predict my outcome once I've removed the variance from my covariates? In other words, I've removed that noise. So we're definitely going to use this variable when we have covariates. This also is probably going to be interactions, because we're not necessarily interested in the interaction between two variables unless they explain above and beyond the individual relationships between their component parts. So again, if we have a model where we have depression and anxiety on school performance, and we also want to look at the interaction, we would put depression by itself, anxiety by itself in the first block in a hierarchical model. In the second block, we would add the interaction. So that basically says is once you've accounted for the individual prediction of depression and accountability, is there something left over in that interaction that needs to be accounted for? And if not, the interaction, even if it exists, isn't important to me, because I don't want to use an interaction if it's not adding to what I already know from the individual effects. So also, this is definitely going to be theory driven. We need to have theory behind why we're using these various blocks. But within these blocks, we have a lot of control over what we can look at. Finally, we have the truly statistically driven or systematically driven technique. So this is actually a much more modern version of the multiple regression, and this really comes from the advent of computers, where we actually kind of take multiple regression to the more of an iterative approach. The only thing we now have to tell it is what direction it's looking for. So again, it can be used for the above predictions, but we're usually going to use this when we have less theoretical reasons or we're not using covariates. So again, it's kind of similar. We have a bunch of predictors. We expect them to be related, but we don't have as strong a theoretical model to expect why certain predictors should be entered first, and we're not necessarily looking for covariation. And the 3 times of this is backwards, forwards, and stepwise. And forward simply means I'm going to put in the very biggest predictor first, and then the second, the third, the fourth in order until they don't make the model better. Overall, prediction stops getting better when I enter this variable, and at that point I'm going to stop. Now the problem with this is occasionally I might miss something. So if I have 5 predictors and the first one, the largest predictor individually, is significant, it goes into the model. Then forward would look at the second biggest predictor individually. If it significantly adds to prediction, it's added into the model. It then looks at the third predictor, and again, if it's statistically significant and it adds to the model, or it adds to prediction, it's added to the model. Now, if the fourth one turns out to be significant, but at this point adding it to the model does not increase prediction statistically, we wouldn't add it and we'd stop. Which means that if the last predictor, which was the weakest predictor, but actually was a unique predictor that didn't share any variance with the others, while the fourth predictor, actually, the reason it wasn't significant was that it actually shared variance with other predictors that were already in the model, we might miss something with forward. Backwards does it the exact opposite. It puts every single predictor in the model all at once, and then it keeps pulling them out until it finds one that when it pulls it out, it doesn't make the model worse. In other words, if it starts with all 5, it's going to pull out the 5th one. And if pulling out the 5th one does not statistically significantly change how good the predictor is, it's going to keep it out. And it's going to keep doing that until it finds, if I pull this variable out of the model, the model actually gets significantly worse. And at that point, I put that back in. Now, the same thing can happen. We can end up where we stop pulling them out after the third or fourth one is removed, but there's one further down the line that probably should be removed. So what I'm trying to communicate is both of these techniques tend to occasionally miss a relationship. So they're a quick and easy way to look at data. They're statistically driven, but they also can make mistakes in certain situations. Stepwise is a technique to kind of get around both of these problems. And what stepwise does is it goes backwards and forwards. In other words, it goes forwards, so adding the biggest, and then the next, and then the next, until it doesn't add anymore. But then it doesn't stop there. It actually then does a backwards regression to try to basically find any missed variables that might be in there. Again, this tends to be the way we're going to go. So in most cases, if you're doing a systematic statistical regression, I would say stepwise is the way to go. But ideally, where we want to be is the hierarchical regression. You want to be making these decisions yourself. You shouldn't be relying on statistical techniques if you've got theory behind you. So let's just kind of look at how these differ. So again, entering all at once, the enter method, we just enter them all at once. We only look at unique variance explained in the outcome. We don't look for any shared variance. Hierarchical model enters it through blocks based on theory. And then we have, including based on the strength of the relationship, the statistical technique, either forward regression, backwards regression, or stepwise. Now, this is someplace that a lot of students get a little confused, so I want to stop here and get your attention. Hierarchical models are theory-driven where you're in control. However, in each of the blocks that you control, you may be adding more than one variable. So in a hierarchical model, if I've got 3 predictors in a block, I still need to decide within that block, do I use enter, forward, backwards, or stepwise? And this is what confuses some students. This doesn't mean you're doing a forward, backwards, or stepwise regression. You're doing a enter, forward, backwards, or stepwise decision within a hierarchical model. And again, I would say all things being equal, go with stepwise. So again, if we are actually choosing which variables go into blocks, those blocks are being decided by us, we're making the choices, and those choices are based on theory and our own special knowledge. That's hierarchical modeling, and that is where we ideally want to be when we run multiple regression. But if we have a block within a hierarchical model that has multiple predictors, we do have to decide how we treat those predictors within that block. And that could be enter method, unique variance alone, or we could look for all of the variance in the outcome within that block, going forward, going backwards, or stepwise. Now again, just as a reminder, if we're going forward through a data set, we might have GRE as our biggest predictor of graduate grade performance. Undergraduate GPA is next, their personal statement is third, and their CV is fourth. And this is basically done with just correlations. A correlation matrix outside of the regression found that GRE by itself is the largest unique contributor to graduate GPA, followed by undergraduate GPA, followed by statement, followed by CV. So a forward regression would look at GRE and go, is it significant? Yes, it is. Cool. I've got the start of my model. It would then add GPA, and it wouldn't just ask, is GPA a significant predictor? It'd also say, does adding GPA to GRE get me a better fitting model? Is it a significant improvement in my ability to predict your outcome? And in this case, the answer might be yes. It then would look at statement and find actually statement did not. And again, we might then go forward to the CV, but we're going to miss the CV here. So CV isn't going to be missed because it's not even going to be looked at in a forward regression because statement was not a significant improvement to the model. Therefore, even though CV was, we would miss it in a forward regression. Backwards regression would start with the CV, notice that it's not significant, and then would find that the only thing you can remove from the predictive model is CV. If you remove anything else, statement, GPA, or GRE, the model gets worse. And again, in this particular case, backwards would get you a better goal than forward. But there are situations where backwards can miss something, and that's why we might want to use stepwise. Also recognize again that the interpretation of linear trends and covariates, generally speaking, if we're looking for nonlinear and linear trends, if we're looking for covariates, we shouldn't be using forward or backwards or stepwise or enter. We should be using hierarchical. So here's just an example visually with a Venn diagram. If we're using enter method, what we're seeing is the unique variance. So the only way a variable is going to be found significant and a part of a predictive model in the enter method is if it actually predicts uniquely outcomes. So I have three predictors, x1, x2, and x3. Their unique contributions to y is what an enter method is going to be. And this isn't necessarily a bad technique if your question is exploratory, and if what you're really interested in is are they uniquely predicting the outcome. Now moving to hierarchical, we might actually tell SPSS, we might tell the multiple regression, I want you to look at predictor 1 in block 1, predictor 2 in block 2, and predictor 3 in block 3, because I have theoretical reasons to believe that x1 will be my biggest predictor, followed by x2, followed by x3. Now in reality, they're almost all equally contributing to the prediction of y, but we're now telling multiple regression where to give that shared data to. So in this case, x1 is going to explain the most variance in y because we've told SPSS that's what we want you to look for. And again, that shared variance is going to be included. When we then add x2 in block 2, it can't get at that variance that's already been attributed to x. Now x2 has got what's left. Now notice that x2 is going to be a much stronger relationship in the hierarchical regression than the previous slide when we were looking at it in the enter method. And finally, x3 is only going to be able to account for variance that the other two have not already accounted for. So that's an example of a hierarchical regression, theory-driven, and then in blocks, x1 in block 1, x2 in block 2, and x3 in block 3, we've ordered who gets to get first crack at that shared variance. And you'll also see that these results would be different than that enter method. You're going to find all three of these variables actually, except for x3, are going to be given more relationships. In other words, they're going to be found to be stronger relationships than we would have with enter. Now the forward method might find a completely different result. The forward might find that x1 is still the strongest predictor, so it lets x1 gobble up the shared variance, but it might find that x3, even though theory didn't expect it to be, is slightly stronger of a predictor than x2. So it may actually give all of the shared variance from x2 to x3, and then find that x2 is not significantly related. In other words, forward might tell us the solution is x1 and 3, get rid of 2, where our hierarchical method found all three were predictors. So I hope this helps you kind of get a grasp for why your choices are going to affect your outcomes.